Hi, in today's video we will discuss the significant figures and their use in chemistry. In this you will learn why significant figures are used in measurements, how to count the number of significant figures in any measurement, how to determine the number of significant figures to report after you perform addition or subtraction or multiplication or division, and how to determine the number of significant figures when you have a complex series of calculations. What are significant figures? Significant figures are those numbers that are reported whenever a measurement is made. This is a way we can look at the quality of any given measurement. The greater the number of significant figures, the more precisely the measurement was made. Look at the example of the two measuring devices. When we make a measurement using analog tools, we count the number of divisions between the major markings. So for device 1, we see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 markings in between 0 and 1. And in device 2, there's only 1, 2 markings in between 0 and 1. We then look to see where the object we're measuring falls on the scale. And you can see here it's a little past 1, and we always estimate, it's not quite to the 1.1 mark, but we always estimate past the smallest division, one digit past the smallest division. So you can see in this measurement, we're recording 1.08. And in the bottom measurement, well, we can't tell how far it is between 1 and 1.5, so I mentally tried to make a division at 1.1. The numbers in these measurements, 1.08 and 1.1, represent the number of significant figures in the measurement. Because device 2 has fewer markings in between major devices than device 1, our measurement is going to have fewer significant figures for device 2 than device 1. So why all the fuss? Well, when we measure things, we do not want to overstate nor understate how well our measurement is made. For example, if you have a bank account, and in that bank account you have $572.21. You would be happy if your bank told you that you had $572.21. But would you be happy if your bank said your balance was around 500? Or would you really understand what they were meaning if you got a statement in the bank said that you had $572.2102,304? Measurements need to be made precisely, and that is what significant figures tells us. There are rules for counting the number of significant figures in a measurement. We will need to count the number of significant figures in any given measurement so that we can judge how well measurements are made. We will also need this knowledge when we start doing math with our measured values. These rules are as follows. Number 1, any non-zero digit is significant and needs to be recorded. So anything that's not a zero, you have to record. Zeros fall into one of three camps. The first is leading zeros. Now these are at the left of non-zero digits, and these are never significant because they are placeholder digits. An example of something that would be a leading zero would be in the number 0.015. They are to the left of the non-zero digit. They are holding the place and are never significant. Captive zeros are between any two non-zero digits, and captive zeros are always significant. An example would be something like the zeros in 1,005 meters. Trailing zeros occur to the right of non-zero digits. Now these are sometimes significant. They're significant if and only if there is a decimal point in the number. So the 0 in 1.50 meters, that 0 would be significant because there is a decimal point. Or 100 decimal point meters would be another example. However, in 100 meters, those trailing zeros, there's no decimal point explicitly stated. Therefore, those zeros would be insignificant or not significant and would not be counted. Let's look at some examples. The first example, 123 meters. This has three significant figures. Since all of the digits are non-zero, they are significant. In the second example, 100.23 meters has 5 significant figures. The non-zero digits and the 2 zeros in the middle are captive. Therefore, they are significant. In the next example, 0.043 meters, this has 2 significant figures because these zeros are before a non-zero digit. That means that they are leading zeros and are never significant. In our next example, 0.04040, now we have all 3 different types of zeros in there. This one's kind of tricky. We have our leading zeros, these are never significant. We have a captive zero, that's always significant. And we have a trailing zero. The trailing zero is significant if and only if there is a decimal point in the number. Therefore, the significant digits in this example, we have 4040. In other words, we have 4 significant figures. In the example 430 meters, we have 2 significant figures because that 0 at the end is a trailing zero, and without a decimal point, that is not significant. In 430.0 meters, this is 4 significant figures because there is a decimal point and 2 trailing zeros. Now that we can count the number of significant figures in a measurement, we can see how we use them when we combine measurements mathematically. So let's use an example with a calculator to multiply 2 numbers. If I multiply 22.1 by 3.4, my calculator will give me the answer 75.14. Now, does this make sense? The number of significant figures in the answer is more than either of the measurements. This means that we need to deal with significant figures when we do math because our calculator just does the math assuming every digit is significant, but is that always the case? So we will have some rules that we need to obey when we are doing math and significant figures. The rule for addition and subtraction of significant figures is that the number of significant figures in the final answer depends upon the least decimal place in our measurements. For example, if I want to add 2.5 inches and 4.31 inches, the least number of decimal places is in the measurement of 2.5. The one's in the tenths place. The 4.31 has numbers in the ones, the tenths, and the hundredths places. Now if I add these together, I obviously get 6.81 inches. But I need to round the answer to the least decimal place of the measurement, which is, in this case, the tenths place from the 2.5. Therefore, our answer should be 6.8 inches. So the easiest way to remember this is to line up your additions or subtractions to the decimal place. So for this example, look, we see the last decimal place is in the 5, the tenths place. So we can just cut our measurement and take all the numbers that are significant. In this case, the 6.8. So let's do some examples. If we want to add 10.12 and 3.2, when we do this, where are we going to cut our measurement at? So I'm going to just draw my line past my decimal point in the tenths place in the 3.2 because that's the least decimal place. If I do that, when I add this together, I get 13.32, but we're going to drop that 2, so 13.3 is the answer rounded to the correct number of significant figures. What if we add 8.356 and 11? Now, what this tells me is my ones place is where I'm going to have to cut off my number. So if I do the math here, I get 19.356, but that 356 gets cut off because it's too far out in the decimal places. So the answer here would be 19. This next example is tricky because where is my least decimal place? It's not where you might think it is. You might think to drop it at the ones place, but instead it's actually at the hundredths place because, remember, those 2 trailing zeros are not significant. So the only significant digit in this number is the 1. Therefore, my answer can only be 100. Now, in the last example, 62.15 minus 31.15. If you do this on the calculator, you get the answer 31. But notice, they both have the same number of decimal places. In order to keep that bit of information about our measurements, we have to add those two zeros. So we cut it out, 31.00. 31.00 is the number we should have, not just 31, because we need to make sure that we have the correct number of significant figures in our answer. The rule for multiplication and division is that the answer should contain the same number of significant figures as the measurement with the least number of significant figures. So we've already seen the example. If I multiply 22.1 by 3.4, the calculator reads 75.14. But our numbers that we're using have 3 and 2 significant figures respectively. So our answer should not contain 4 significant figures. It should be rounded to the least number of significant figures, in this case 2. Therefore, our answer should be written as 75 to the correct number of sig figs. So let's do some examples. If I multiply 12.15 by 6.32, how many significant figures should my answer contain? Well, 12.15 has 4 significant figures, and 6.32 has 3 significant figures. Therefore, my answer should have 3 significant figures. And the answer, if you do the math, comes out to be 76.8. In 18.01 divided by 3, I've got 4 sig figs and 1 sig fig, so my answer should only have 1 sig fig, which gives me an answer of 6. Now if I have 12.1565, which has 6 significant figures, and 2.143, which has 4 significant figures, my answer should end up as 4 sig figs, and it should be 5.673. When dealing with complex calculations, first we have to remember our orders of operations, or please excuse my dear Aunt Sally. Parentheses, exponents, multiplication, division, addition, subtraction. Now remember, in multiplication and division and addition and subtraction, those two sets of operations, multiplication and division and addition and subtraction, hold equal weight. When you have equivalent operations, we always evaluate our function from left to right. Now don't worry, that situation is very rare in introductory chemistry. So, to determine the number of significant figures to report in a complex calculation, first carry all numbers as significant. Do everything as if they are going to remain significant. You never deal with the significant figures until the very end. Then you need to evaluate each step for how many significant figures it would yield. So in this example, if I want to evaluate this calculation here, 22.15 plus 3.2, divided by the sum of 2.115 and 1.122, if I use the calculator, I carry through all the numbers, I get 7.8313, etc., and more. Now, however, that's not the right number of significant figures. I should not report that. What I need to do is go back and look at each step. Now, we start with the parentheses because that's the first step in our order of operations. So I'm going to evaluate what's in the parentheses first. Here we have the 22.15 plus 3.2 in the numerator. That addition gets carried to the tenths place, because remember, addition goes to the least decimal place. And so the answer of that would actually have been, if we kept that as the significant figures, 25.4. And in the denominator, because they both have numbers to the same decimal place, the answer for the denominator would be 3.237. Finally, we have the division. The top of the divisor has 3 significant figures and the bottom has 4. So my answer should be rounded to 3 significant figures and reported as 7.83. So by now, you should be able to answer questions regarding why significant figures are used in measurements, how to count the number of significant figures in any measurement, how to determine the number of significant figures to report after performing mathematical manipulations such as addition, subtraction, or multiplication or division, and how to determine the number of significant figures to report from a complex series of calculations. Now make sure you watch the video again if anything is unclear. You may also contact me if you need further clarification on any of the concepts you have seen here. Now, one thing to remember is the only way to actually learn this material is through repeated practice of problem solving. You must do many different problems in order to gain confidence and competence in correctly reporting your number of significant figures.